I'm John Swanson. I'm currently working as co-chair in the IP-XACT users group, or best practices group as we like to call it. I've been involved in IP-XACT since the early days of the Spirit Consortium, which some of you referred to as that European club that was working on this that you didn't care about at the time. But it's come a long way. So I'm going to talk, as I said, about 15-20 minutes about how IP-XACT can be used to improve verification. Now, I work for Synopsys, and in my role in Synopsys, I manage lots of the IP. Basically, I manage everything without a PHY, so mathematical, networking, all those kind of things. I also manage the IP tools and IP-based design flows for Synopsys. So I see a lot of different things. So I'm going to talk about why we're looking at this, and I'm going to share some data, some of it public, some of it from Synopsys. How many people in here are familiar with what IP-XACT is, have already used it? Okay, so a few people. So for those of you that are already familiar, I apologize. You're going to find this section a little bit boring, but there's not that much in there. And then I'm going to talk about how it can be used specifically for verification. So why are we looking at it? Well, you guys know this better than anybody else. Consumer electronics has gone crazy. I got my wife an iPad last year, and she loves it. It's got video, it's got games, it's got 3G. Pretty soon there'll be one with 4G. But everything is connected. Everything has to work together, and this has brought a lot of different IPs together. And it's not just the consumer products that are suffering from this. Think of your networking providers. Look at the data centers that companies like Facebook and Google are doing, and the kind of chips that are running in these servers now. I mentioned I work in networking IP. We're already talking about terabit Ethernet. We just got 40, 100 out, and it's not fast enough for these companies. So it's media everywhere. Everything is connected. Now, I find 140 devices per person a little bit hard to believe, but then I went shopping for a refrigerator. Imagine my surprise when these really nice refrigerators automatically connect to the wireless network in your house and theoretically can tell you when you need to buy milk. So maybe in 2013, I still question that one. But anyway, this incredibly complicated designs. And what this has meant is in different spaces, you've got multiple IP titles on a single chip. We've got to get the form factor down. There's lots of exciting work going on in that. But everything from MIPI down through Ethernet, all of these things are having to go on the same chip and work together. More protocols, more complicated protocols, faster protocols, and many companies are trying to build chips to target multiple generations so you don't have to redo the chip. One of my favorite ones is in the wireless space right now. You want a wireless everything chip. It's got to support all the standards. And the next generation is going to have to go out and support everything the current ones do, plus LTE-A. So you're going to have 5 different radios on the same chip. Really complicated. Consumers are driving it, and companies are keeping up with demand. And you see a lot of designs where companies are going through changes now to change the infrastructure. So you look at the microwave cell phone tower. There's a new Ethernet standard called Carrier Ethernet, which companies are putting in the microwave towers. It's not changing what you get on your phone, but they're able to process those games your kids are doing quickly. Now, I'm in the IP business and tools business, and we tend to talk a lot about the verification. And you're here to learn about verification. And I think you know this part really well. The RTL verification, the IP qualification, the RTL development is a huge amount of the time. But when you're looking at all these different protocols having to work together with multiple processors, software is by far one of the biggest things. And IP-XACT can really help you here. If you've got documentation of all the registers, well, as soon as you get your RTL configured, and you can hand this off to a software development team, you're able to bring everything in. Instead of having to wait until you've got RTL, you can start pulling these design cycles in. The ESL guys have been talking about this for years. You can do it, and IP-XACT is a great way to move information amongst the different design teams. How important is software? Well, it's approaching about 50% of the effort. So this is from a Synopsys survey in 2010, and hardware was about 54%, but software was at 36%, and this is growing. And I guarantee you that the 2011 and 2012 data will show software as an even larger component in the design. And yeah, some of you have missed your schedules. We see it all the time. We see projects canceled, we see schedules not done. So from a survey, the same survey in 2010, only 26% of the companies said there was no delay in their project. And you think about what a delay can cost your company. You know, if your competition gets that product out first with better software. And you look at mobile phones are one of my favorite examples. You know, a lot of them have almost identical hardware on them. It's the software that makes the difference. Early tape out, only 3%. That hardly ever happens anymore. 2 to 3 months, greater than 3 months. See, that's over 37% of the designs from people we surveyed were late. What is a 2 to 3 month delay costing your company? And you're here at DVCon because it's your job to verify this stuff. And there's a lot of different things you need to think about. They're all little pieces. Did you hook it up to your bus properly? I see cores hooked up to on-chip buses, whether AMBA, your own internal OCP, incorrectly all the time. And people don't catch it in their verification. Will it work properly? If you're doing a high-speed networking, 40 gigabit Ethernet, does the CPU interface with it, and you have a PCI Express? Does all this stuff communicate together? Is your processor sitting there waiting for something to happen? One of the big problems in networking, gigabit became a consumer marketing requirement, and people are having a hard time getting gigabit throughput on their chips. Will it work in your technology? Boy, they've shrunk the geometries quick. I love talking about that. We're not going to talk about that today. Will the core do what I want? You're taking an existing chip and you're updating it. You're going from USB 2 to USB 3. And all the changes at that. Is it going to do what I want? Will it meet my performance goals? Can I get gigabit? And can I use it in my own tool environment? And your tool environment, I'll bet, is a combination of different vendors' tools, your own processes, your own rules, a Perl script that some guy wrote 5 years ago that gets updated. All those things need to fit together. So with IP-XACT, if you know how your components are configured, how they're configured to operate, the register maps, the address space, all the interfaces around them, and yes, what language the blocks are written in, because many of the chips are in multiple languages, you can do a lot to streamline your verification flow. So with that, what is IP-XACT? It's not rocket science. It is an XML schema. That's it, an XML schema. We worked really hard to build the schema to have what was needed. We also included a generator interface called the TGI. And some of you may be familiar with that. We'll talk a little bit more about that. It's in use. I don't know how many people here are using it today, but I can tell you there are a lot of big companies that are using IP-XACT in various aspects of their design flow, whether it's verification, documentation, software tools, things like that. It's a electronic data book of all the IP that goes into your chip with all the information about how that IP is configured. So let's take an example of a Synopsys PCI Express core. I think the base core has 10, 20,000 configuration options. But you, when you configure that core, are only using one set of configurations. So rather than pouring through our data book to try and figure out what goes in your data book and what you need to verify, you have an IP-XACT view that documents how you configured that core for your design. So what are the registers? Where are the memory addresses? All those things. And you can give it to the other people that are part of your design flow. When we created this originally, one of the big things was it has to be design language neutral, because there were the Verilog guys, there were the VHDL guys, there was this new thing called System Verilog that was sort of, early days back then. And then there was C, C++, System C, and everybody gets real emotional about design languages. Well, we didn't want to get involved in that. So we picked XML based on the W3C standards, and we developed a standard that is language and tool neutral. And this is really important, because if we did a survey, we would see something like this. Now this is one, it's a little bit old, it's from 2009, VDC research, but what leaped out at me is I found this for another project I was working on, was what languages people are using for their verification. And as you can see, it's all over the place. So is implementation, interestingly enough. But verification, it's just all over the place. So in developing the standard, if we'd come up with something that was kind of leaning towards Verilog or leaning towards System C, it clearly wouldn't have met the requirements of the designers. So it's a good thing we had really good religious conversations about staying language independent. What is a schema? Well, it defines the logical building blocks. Now, you can download the IEEE spec from the web, and I think it's about this thick, and you can read it on the airplane, and it will help you go to sleep, because it's a really detailed, good, boring specification. The schema defines how it's all put together. Now, I recommend you learn XML by using a tool. You can Google XML editor, you'll see tens of thousands of hits. Personally, I like XML Spy. I'll give them a plug. It's a very nice tool. But it shows you graphically how all the different elements fit together. Which elements are childs of others, how they have to be ordered, whether it can include text or the legal values for it, the data types. All of this information is used to document the IP. That's very important. XML does not do anything. Dig up one of those old Spirit marketing presentations and they'll talk about all the problems that IP-XACT, or Spirit as we called it in the original days, was solving. XML doesn't do anything. It's text. It's created to store and transport information. If you look on the internet, you will see tons of XML streaming. I have another slide I use sometimes that shows the Apple XML use, an iPad, an iPod, an iPhone. All the music is documented in XML. And depending on which device is reading the information, they use different parts of it. If it doesn't have the ability to display the album cover, we don't use that in our software. But we use the same source to drive all the devices. You created your own tags. There are no predefined tags in XML. And there's lots of different schemas out there targeted at lots of different things. IP-XACT is an XML schema. We want to see all the components are in there. We might want to connect some monitors in the test bench. So we need to know where they are. With these components, what do we document? We document memory maps, registers, bus interfaces, all those things that are relative to a component. And then in a design file, we'll document how the component is put together. So this is why we're looking at it. This is what it is. How can it be used in verification? Well, let's just take a typical system on a chip. You've got a processor bus, which is really high speed, which may have some new memory, may have some new logic. You've got kind of a high-speed peripheral bus. This is where your USB might be connected. You've got a lower-speed peripheral bus for the UART and things like that. You've got to verify it. So you've got verification IP. It might be something you purchase from a company. It might be something you develop. You, in our traditional RTL verification, need to do interface and functional testing. So how could you do that? Well, here is that ugly schema. I love to call this ugly. I continually run into people that want to write this. It's worse than assembly code. So if you're going to process it, the first thing you need to know is what's the version of the schema. Now there'll be a lot more stuff here in real. I cut it off so it would show on the slide, but you can find the element that tells you what version of the schema, because there are several versions out there and not everybody has moved to the IEEE version. What is the name of the design and what version is it? So once again, we know the schema, we can go down, we can find the name of the design. What are the interfaces associated with that design? So here we find bus interfaces, We have the first one, H clock, a description of it. So once again, information for functional verification and information for documentation. And depending on what your IP provider gives you, some of these can be pages long. Again, I've cut it for simplicity. Where are the top level interfaces? I want to, right out of the box, build a test bench that will do a write, read, expect to every register in the subsystem. That's it. I don't want to do functional verification of the USB. I'll do that later. Just to get started, let's make sure we can get to every register in the design. So you can find the bus interfaces and you can hook up the master. We want to see all the components are in there. We might want to connect some monitors in the test bench. So we need to know where they are. How are they connected at the interface level? Not everything is defined in an interface. If you look at what an interface like AMBA gives you, it doesn't give you every connection. There's always those sideband signals. We call them ad hoc. There was no hierarchy when I built this design, so you don't really see it here. But in a real chip, there's lots of hierarchy. And so you can see, what levels of hierarchy do I need to go through to connect things down. Where's the memory map? So here we look for the UART. Here's the address block, start, range, width, all the different bit level descriptions. This is the information your software engineers need to get started. So based on RTL configuration, you have this XML file, you can give it to the other people, you can use it in different tools. And at the session later today, you'll see there's vendors that do provide tools. So how do you do it all? Once again, that's part of our job in the EDA industry to help you do your design. But you've also got the TGI. You can expand, you can customize, you can parse this information. Generators are very powerful. A generator is exactly what you think. An IP-XACT design environment has to have a TGI interface. The generator plugs in. At some point, the tool invokes the generator. The generator says, yeah, okay, I need some information. What that information is depends on what you're trying to do. Maybe you're trying to connect a verification monitor into your design. So the generator says, okay, I've got the VIP here. Where do you want me to connect it? Pass the information back to the generator. The generator runs and will enable more automation. You might have a library of USB vectors and you want to start running them to quickly develop. You might want to set up different views. You might be doing more software and you don't want to develop software on RTL. They could also be attached to a component. You might have something you do only when a certain component is specified. That might be specific tools to run to meet your timing, power. It might be something as simple as make sure it's the latest version. So another great example is changing views. I've talked about the registers. I've talked about the software. Now you may be going to hardware to do that. You may be going to TLM level models, high-speed C or system C models. So you can have multiple views of an IP and swap them out. You can control, I want this block to be RTL, but I want the other blocks to be C, and start doing bandwidth testing in software. You can move into compliance and prototyping. Now, in the IP business, when we take a specific title for compliance, we have to build hardware. Now, it might be in an FPGA prototype, and this could be as simple as a different view. If you think about putting 40 gigabit Ethernet on an FPGA, yeah, you're probably doing some things with the buses because you're not running that super high-speed clock on the FPGA. So you might go into an FPGA prototype, and if you're a bigger company, you might do a whole development system that you would use to take your chip to certification. And many startups today are being forced to do their first development system using an FPGA and bring that system to the market. And if it's successful, then the venture capitalists will give them more money. So to wrap it up, IP-XACT is the information you would expect to find in a data book. It's a schema that we developed. It's language and vendor neutral. You have a generator to build on, and every one of the tool vendors here has probably used the generator, or if you're using their tools, can help you with the generator. It's very easy to process, and it doesn't cost you a lot of money to start using it. Your IP vendor is probably providing you with the IP-XACT today. We just don't talk about it that much. Because in the IP business, it's about features. If we don't have the features you want, you don't want our IP. If we have the features, we should provide this as well. And we do.
Everyone, so myself Kamlesh, presenting here a use case study that applying IP-XACT in the verification domain, how to automate the verification aspect, different verification aspect to using IP-XACT and improve your design. So the agenda will be like just an introduction of the typical challenges what we see in the verification today, and what IP-XACT basically offers for the verification requirements, and how we are using this offering from the IP-XACT to apply this IP-XACT for the verification automation. And then there are some challenges with the current version of IP-XACT and how we are currently addressing these challenges, and how we are progressing forward with the IP-XACT Technical Committee in Accelera System Initiative to address these limitations and improve the standard in the next versions, and then the conclusion. For the challenges, the typical challenges what we see today in the verification domain, that we need to develop test benches. We IP integrator need to know everything about the IP. We need some mechanisms to accommodate IP configuration, like John mentioned, generators to configure the IP, especially for the generic IPs. Today we are using IPs from the different vendors, so this is another challenge. We need to aware about the IP implementation changes, plans, and all these things. And there is a difficulty to debug complex interactions between different IPs coming from different vendors. And for the register level, there are many registers in a particular IP or in a particular SOC. There are thousands of registers. How we are handling these registers in different places? You need to write the test cases. You need to write the header files. You need to do the different kind of tests on these registers. There is a cost associated with each register. If you see from the specification up to the final implementation, there is a significant cost involved per register. So if you see, you write almost half a page in a specification, then you write 8 to 10 lines in a header file, you write 20 to 30 lines in the testing of these registers, different kind of test cases you need to write. Then you need to create a register decoder. In the implementation side, you need to create the register banks. So there are a lot of things you need to do for the registers, and you may need to generate some additional things like for the system Verilog code for the verification. So for each register, there is a very significant cost improved, and it affects the productivity and the quality of the designs. And it's more error prone because we are doing all these things manually. And concurrency between design teams. Now what happens if there is one register changes? Now we have different design teams, one handling for the verification, one handling the IP development, one doing some other verification tasks. So we need to keep in sync all these guys together whenever there is a change in the specification, and it is quite difficult today. Addition changes are, there may be some changes in the specification, especially at the initial phase of the development, and they are very problematic and error prone. And you need to also you are writing some test cases for the IP level. You need to write again the same kind of test cases at the subsystem level, and maybe at the same kind of test cases at the SOC level. So there is a need to reuse the test cases, and how we can reuse, it's a huge effort, and we need to define what subset of registers we can reuse in our flow from IP to subsystem and to final SOC. So what IP-XACT offers for the verification automations? We have a single description for all the information, everything in the IP-XACT as John mentioned. So we have single information, and in the current version of IP-XACT, it offers interfaces, port, register, bit fields, component instances, component connections between designs, by which you can easily automatically create the connections. There are configurable attributes, there are generators, there are automatic configuration of the IPs. It also offers automated composition, integration, and configuration of the verification test benches. You can automatically insert the required transactions whenever you are talking at the two different abstraction levels. There are different set of parameters you can define at the design and verification component as per your choice. You can have a design configuration file to change the views as John mentions, and there is an easy interface for generators for different stuff to generate the different piece of code in the complete design flow. Apart from that, for the verification components, it also offers monitor interfaces, white box interfaces, complete APIs for the metadata exchange and the database querying and generator plugins as John mentions. And the most important is the portability across multiple vendors, EDAs, because it's a single common standard. Everybody is using it. You are getting IP from the third party because they are using the same standard to define the IP. You do not even need to know about the internals of the IP while you are integrating the IP or while you are generating the test cases, because IP-XACT is common for all, and language and vendor independent methodologies. Now, for the how we are basically, we have used this this offering from the IP-XACT in our verification domain inside STMicroelectronics, and we are currently using the same verification flow since last 4 or 5 years, and it's under production, and we are using the same flow in the various chips design. So what we basically do, our flow is basically based on the IP-XACT 1.4, the previous version, and the current version IEEE 1685. We have automatic IP packaging in IP-XACT via your functional specification, your SDL, your legacy formats, PMAP, or maybe custom Excel description, because writing the IP-XACT file is not easy. So we have some tools which can read these functional specification, Verilog VHDL files, some legacy formats, some Excel sheets, to capture the data from higher abstraction level to the IP-XACT descriptions. And we have automatic generation of the verification test benches from the specification, from the Excel, from the EDA GUI, etc. We can generate the TLM RTL models of the different IPs and even mix TLM RTL abstractions also. And it's quickly adaptable for any change in the DUT design specification. So whenever there is a change in the specification, because all the flow is automated, you just regenerate the stuff and everything will be in sync. And it's reusable across different design teams and different projects, and design teams are always coherent because there is a single source of information, and whenever there is some change, everything is automatically generated. So everybody will be in sync. So you don't need to put efforts there. So this is just a block diagram where we are using. If you see in the top, there is you have multiple sources to generate the IP-XACT package, maybe from the functional specification, maybe from your Excel sheet, or maybe from some legacy register description. So we generate the IP-XACT descriptions. We have some IP-XACT description coming from the third party, and then we do the platform assembly using some Excel sheets, or maybe using some EDA like Magillem, Atlanta, core assemblers, and others. We have a design XML, and then we again using the EDA netlister to generate the verification test benches from the same IP-XACT file of the component description, which contain the registers. We have a register test generator which can generate the register test cases, and we import these register test cases in our verification environment. And also there may be some functional verification, we might need some C header files for the register. It is also automatically generated using the same IP-XACT file. And for the functional testing, although of course this is not covered in the IP-XACT, so user need to provide the functional test. So basic reader writers we can automatically generate. So this is the complete flow, how we are generating the verification test benches and creating the register test cases automatically using the IP-XACT descriptions. And you can also capture your design, because when you have a large design, so it's not easy to go in the GUI. So basically we also have a flow based on the XLS tables where we have defined some pre-formats, set of tables to define the connections, to define the different instances of your verification test benches. And then we have some tools which can import the design to create the design in IP-XACT, and then we can netlist it using any EDA netlister to generate the verification test benches. Now going for the register management, again the top part is the same. We generate the IP-XACT from the functional specification, Excel, legacy, or maybe from third party. And for the verification, some EDA mnemonics or some EDA debugger files as well. So because the source of information is same every time if there is a change, so it is quickly adaptable to the specific changes, and it's a single source, so it ensures the coherency between all these domains, because everything is, this is used by software, this is used by verification, this is used by validation, this is used by another debugger, so everyone will be in sync. So this is basically, we have this register info format. We generate the IP-XACT from the registers directly. Then we can generate different source of information whenever what is needed. So we can generate header files, we can generate the test cases, we can generate the mnemonics map. For example, this is shown for the cadence, so we can have another format as well. We can generate the ASM assembly files as well. We can generate the system verilog header files, system verilog test benches. We can generate these C files, C test cases, and other stuff using the flow. Now, there are some challenges we face during this flow, and how we are currently addressing this. All the challenges we have already addressed in our IP-XACT technical committee in Accelera, and probably in the next version, all these limitations will be will no longer be there. So there might be some definition misalignment we have seen from the IPs we are getting from the different parties. So we are trying to put centralize these bus definitions, so everybody is using the same set of bus definitions to create the IP-XACT description, so there is no such ambiguity in the future. It is currently handled by the user group under John. There are some limitations in the IP-XACT, like one-to-many connections is not allowed in the IP-XACT. So we have some solutions, like some media tools allow one-to-many connections with a warning. We are just currently just ignoring the warning, but it violates IP-XACT compliance. So we have a capability through a generator by which you can auto insert some virtual components between these one-to-many connections. We have the IP-XACT description coming from the different parties. Sometimes it contains some errors or some semantic errors, some schema errors. So we have developed a utility called check, which basically check these IP-XACT descriptions. So you can also add some custom checks depending on your requirements. It also does all the semantic checks provided by the IP-XACT standards, all the schema checks in the standard itself. And of course, you can also edit your test cases via simple plugins. And you can just play around, you can convert when you are getting IP-XACT 1.4 from the third party and your flow is 1685 base, and we have a converter, you can easily convert these descriptions to create the same versions. Apart from that, sometimes we get some IP-XACT description which contains only the interfaces specific from the IP designers teams. Sometimes we get the IP-XACT description only contains the register descriptions. They are basically coming from the verification team. So we have different pieces of IP-XACT file corresponding to the same component contain different pieces. So we have a utility by which you can merge these IP-XACT descriptions to have a complete IP-XACT descriptions in a single file. There are some limitations in the current standards. TGI API is not capable enough to handle these generic IP-XACT descriptions, and we have currently addressing these limitations in IP-XACT technical committee in Accelera. So it's not easy to handle configurable IPs with this current version. So we have a solution where we have defined a set of vendor extensions to define the configurability. So as long as you are using the same set of vendor extensions to define the configurability inside your IP-XACT descriptions, you can use the same generator to create the different use configurations. So like for example, you may have some generic IPs in which the number of ports and registers are not fixed, it's a variable. You can have some interfaces, some register present in one scenario, maybe not present in another scenario. And there are many more such requirements where you need to have you might need to have a different set of IP-XACT description for the same component. So instead of keeping the different set of IP-XACT description for the same components, rather than it's the generic IP-XACT descriptions based on these vendor extensions and generate these specific IP-XACT descriptions as and when you need it. So you do not need to maintain all the IP-XACT descriptions corresponding to different configurations. For the registers, as I said, we face some challenges for the configurability. We face some challenges for the side effects. Currently, we are We have added some vendor extensions, and we are addressing this requirement also with the IP-XACT technical committee. So there are some special register behaviors are missing, some custom flows are needed to address some specific needs, and especially for some legacy stuff. And there are some UVM specific needs, so maybe in the next slide we will address this UVM specific needs. So there are some challenges that we face. Currently we have workaround to address these challenges, and all these challenges are already reported to the IP-XACT technical committee in Accelera, and we have already discussed about all these limitations, and in the next version we will have these limitations no longer will be there. So conclusions, as experience from our work, it's simplified integrations, verifications. There is an automatic flow to avoid manual repetitive jobs, maximum reuse, no duplications, quickly adaptable to any changes, ensure coherency between design teams, single source, and we have automated flow to generate the different pieces of information, and it's a standard, so it allows multi-vendor IPs, EDA tool use without any issue.
So today I'm going to talk about IP-XACT and UVM. My name is David Murray, I'm CTO of Duolog Technologies. And it's a very, very interesting topic area, especially when you look at the focus or the interest in things like registers. So we all know that IP-XACT can be used to describe registers and that UVM can be used to test registers. So we're going to have a look at that today and do some deep dive looking at some use cases. So the agenda today then is we're looking, I'm not going to spend much time introducing the standards because that's been done already. John did a very good section with that. We are going to look at the benefits of using the standards together. So in the Accelera, there was what do they call it, the town hall meeting today. One of the questions I think Rohit, you probably asked is that there's a merger of the different standards. There's a merger now with the OSCE, the different standards bodies. OSCE has now been merged with Accelera. So one of the things that needs to happen there is how do the different standards integrate with each other. It's a very, very important topic because the standards development in something like Accelera can be seen as vertical standards. You've got System C, UVM, IP-XACT, coverage, etc., etc., etc. Whereas a lot of the EDA problems can be solved when we start looking at horizontal integration of those standards. And an example today is looking at two standards like UVM and IP-XACT and see how these can horizontally integrate and see the benefits of doing that. The use case we're going to be focusing on is the hardware-software interface. Again, registers is echoing around the room, so we can focus in on that. As the previous presentations have shown, that IP-XACT can be used for a lot of different verification automation activities. And then we're going to just present some conclusions towards the end. So again, I'm going to skip over this very quickly. It's an XML schema. I think John highlighted that one out. UVM, again, what UVM is aiming to do is to deliver, it's focused on delivering verification productivity. So there's a session next door, and that has been going since the morning, all about UVM. It's an advanced verification methodology. It has all the standard verification capabilities, scoreboarding, coverage-driven verification, etc. It has, interestingly enough, and this is sort of back to what John was presenting earlier on, where we saw that the software is becoming the biggest component, the biggest problem. And it's very, very good to see that the VIPTC under Accelera has decided to put in something that helps with the hardware-software integration verification. So UVM comes with its own register package, and it's coming with a set of capabilities built around this register package. And again, the main benefits there are it's an open standard under Accelera. It gives you advanced verification capability and then interoperability and reuse. So the main benefits of using standards together, if we take the best benefits of each of the standards and have a look at that, IP-XACT as an XML schema can be used as a type of single source spec for your IP data. It's a data sheet. So it can contain things like registers, interfaces, ports, etc. The fact that it's a standard means that the terminology that we use is it's standardized. So the terminology we're using It's not like opening up a Word document and typing in, this is a very nice register, and it's a read, comma, write register. There's specific terminology that can be used. And this means that the ambiguities are less, that there's less room for misinterpretation. Also that the schema itself, that it can actually be checked that certain common mistakes are not made. So if you have overlapping bit fields described in your register, descriptions that you can run a check against these and say, no, this fails the compliancy, this is not allowed. The fact it's already been shown that because it's an XML schema, it's machine readable and it's automatable, so we can do anything with these register descriptions. And that's something that I think when we're looking at verification, there's many side effects to this automation, including just improving the whole quality of your hardware-software interface across all the different implementations. UVM then, again, it provides some advanced hardware verification capabilities. Again, we can look at some of the hardware-software interface verification capabilities. It has its own register models, it has its own testing capability and APIs against those register models. So if we can leverage the two standards together, we can get a significant level of verification automation. So what we're going to do is we're going to do a deeper dive into the register descriptions and into the IP-XACT and sort of how they hook up and what is the alignment, what is the misalignment. Okay, so a very, very quick overview of the hardware-software interface. Typical IP component block module. On the left-hand side here we have a processor interface. This burns a hole in the screen. So we have a processor interface. Again, it could be AXI, OCP, APB, etc. There is a protocol decoder here, extracting the address information, and then there's a set of registers here that basically that information is written into, and that these bit fields are actually communicating with a logic block. Also, there's status information coming back, or information from the registers also coming back when this is, so you can have both write and read operations. There are some nuances with this, which is the nuances always, the devil is in the detail. So some of the nuances here is again what we're looking at the interaction between hardware and software. So there's lots of optimizations here which cause different side effects and different types of behavior. This is just an example of one where what we do is we want to read the interrupt bit. So yes, we get a read, but then typically what would happen is will we write it as 0 to clear this, as in actually write back into it to clear it. Whereas what we're doing here is when we read it, we're actually going to clear it. So this is it's called a side effect, or it's called a read behavior, that when I'm reading something, there's additional behaviors here. And there is, if you look at all the designs out there, there's probably thousands of side effects, and some of which we're standardizing, and some of them which are just too strange to even contemplate. Read twice to clear, or all these types of highly creative designs. So there is a sort of a defined set that are very, very common, and then that tapers off to some of the more creative ones. Okay, so this is an example of what you would see in a document, except for you'd never get this colourful. Really, that's the benefit of using PowerPoint. It's usually a little bit more boring. So forgive me if I've offended anyone's sense of fashion. So what happens is this is a register description. Typically, it's a register. It's got some bit fields here. It's got it's going to be a name on the register. There's going to be a reset value. It's going to have an offset. It's going to have an access type, read write, read only, etc. It's going to have these different bit fields again with more information. So there's quite a lot of complexity, especially when you think every single field here could have its own access type, its own reset, its own nuances, its own types of behaviors. So when you start combining all this, it can get complex, because if it wasn't complex, there wouldn't be any problem with it, but there are problems with it. There are problems with trying to debug the hardware integrating with the software, and this is usually the first level things go wrong. So if we can clear the decks and get the quality of the hardware software interface up at the IP level, it streamlines a lot more of the hardware software interface. From a UVM point of view, UVM contains it's a set of classes which can describe registers. It can describe registers in a memory map. This is sort of a very, very high level view of the UVM register class construct. You have a block which can have registers. Registers can have bit fields over here, and then it combines basically some attributes and some methods for actually defining these. So the main thing is what this means is that if we can define this model in UVM, you're actually defining the behavior, expected register behavior of a DUT or a DOV, I think as they start calling them now. And with this then if I can define register behavior, I can start automating it. So this is already in UVM. There's a lot of work done on it, and again it shows the seriousness, I suppose, of ensuring that your hardware-software interface quality is up there, that the EDA, the standards bodies and the EDA vendors, etc., have gone to this length of actually producing these types of models. So if we look at this, this is a sample environment. Over here on the right-hand side, we've got basically the DOV. It's got some registers, it's got some type of slave interface, etc. Then we have a verification component here, which basically can drive specific transactions into this particular interface to access these registers, or if there's memories, etc. there. We've got a sequencer which actually is executing the sequence of events that are happening. And over here then, in this part, we've actually got the register model, which is like a shadow of the registers inside this particular device, the device under test here. So what happens is it's very easy to basically abstract, and this is what UVM does. We can actually, because there's a register model here, we can actually start. It gives you a high-level API where you can actually start accessing, via a sequencer and a sequence, you can start accessing these registers from your verification environment. It also comes with a set of built-in test sequences. And what these can do, if anyone's designed IP before with the basic programmer's view of it, we've all done let's write ones and write zeros and read back and make sure that the hardware-software interface is behaving as expected. So this is being done. I've done it in many different languages, etc. And finally, with UVM, they actually provide these built-in test cases. Because the content of the behavior, the expected behavior is known, then these can run generically. That means that if I define a register model for a particular device under test, and I have this verification environment, I can run a reset test case out of the box. Read all the registers and see if their values are expected. Without having to write any test case, I can just call the built-in sequence. So an example of looking at the IP-XACT UVM mapping is we're going to look at the stat bit field here. So again, so there's a name, there's an offset 4, and the bit width is 8, and it's a read-write access. So in the UVM, this is what the UVM register model looks like. This is we're basically defining a class for the register which extends the base level UVM register class. We're describing 3 register fields: reserved, stat, and control. We're actually inside these different functions. Then we're creating we have a function here creating the register, and then we have a function building the register, which is actually creating and configuring the different bit fields. So this is creating a bit field, and this is configuring the bit field according to the different types of attributes here. So for instance, it's configuring, the stat is the name of the bit field, it's configuring it. 8 is the width of the bit field, 4 is the offset, and RW is the read-write. So UVM has its own terminology. It's not the same as read-write, read-write. So it's an example of things that need to be translated, and sometimes there's a one-to-one, sometimes there isn't, sometimes there's little nuances, etc. But essentially, you want this to generate this type of infrastructure. If you think this is bad, you don't want to be writing this by hand. Okay, because again, typically I think we've seen it in the industry, one register is 100 lines average, 100 lines of UVM code to describe a register, and if you've got 1,000 registers in your subsystem, I won't say chip anymore because that would be insulting to some chips. But if you have 1,000, it's a day for a register. There's several metrics out there. You want this automated as much as possible. In terms of just looking at some of the examples, this is actually in the UVM user guide as well. What happens is this is basically just showing you mappings between the different access types. It's quite detailed, and I won't get into everything, but just shows you that in UVM you just have a single access type, which is type of aggregated of read and write type of action. So this just shows the mapping between for access equals read and write, for the different read actions and modified write values, how to translate to UVM, what the actual UVM value is. So for instance, this one is, I'll take this line here, the write value is 1 to clear, and the read action is set. So the actual UVM is W1C or S. So again, you don't want to be typing this by hand. You want these type of translations to be automated, and this is what the UVM generators will do. So looking again, just taking one level up and looking at the memory maps, one interesting thing is that just to show you some of the nuances, in IP-XACT the register has the actual address offset, and in UVM it's actually the offset doesn't belong to the register, it belongs in an actual map. So this shows you a register block for USB. This is a sort of a snippet of it, and we can see there that the register here, you're actually creating a map, and then you're basically adding to the map the UTMI event register to 88 hex, and it's a read write, etc. So this is a snippet of IP-XACT USB memory map, and again it contains the register which we've seen previous, and this is the actual the UVM, the corresponding UVM. So again, what happened is when the VIPTC were developing the UVM register model, they did take the IP-XACT register schema into account. So there's a very, very close alignment like what we've seen. There are some areas where then the IP-XACT wasn't covering all the verification. So there's a few areas there where there was sort of, some things are not in IP-XACT that would be needed in UVM. So some things was the HDL path to registers. So there's my surprise in terms of how do we do that, and we can go through some solutions about how you can actually do that currently today in IP-XACT. Also multiple resets, so there was a multiple reset here as well. So we've heard a lot of the design community come back with these type of requests. Coverage control, how is it possible to basically put coverage control in my IP-XACT so that when I do generate my register model, there's specific coverage configuration, cross coverage configuration scenarios. Verification attributes, I want to be able to say, look, do not run, if a reset test case is run, I do not want to run on this particular register. So you can actually add that as a verification attribute. And again, other register types, indirectly accessed, alias mirrored, FIFO type registers. So the good news is these can still be handled with IP-XACT by adding vendor extensions, and which are going to be covered under standard extensions, which is our next presentation. And that means that you can basically add on basically for the HDL path, you can add on a HDL path type of extension that can define the actual HDL path to the register. Also, we're going down the standardization route. So what happened is roughly a year ago, we basically, coming from the VIPTC over to the IP-XACT TC, we brought all these types of requirements from the VIPTC about, well, what do we, from a UVM, what does UVM want to see in IP-XACT? So all these requirements have been brought into the IP-XACT TC, so we're working on these currently. And again, you can see there some of the requirement numbers and the types of requirements that there are. So this is and actually where they're ending up in terms of the different working groups inside an IP-XACT. So it's a very good example of within Accelera, the different standards committees working together to make sure that you have more of a horizontal integration of the standards. So the main benefits, again, IP-XACT as a single source spec for IP can be used to automatically create verification collateral. You're going to have fewer specification bugs because you're not going to be allowed to make them. They're going to be caught at source rather than caught. I think someone mentioned they're always going to take 3 months to capture my IP registers, etc. It could take you 3 months to find that bug in the lab, just as easy. And a few of us have been there before as well, in terms of, especially in the lab, nuances between the hardware-software interface are very, very difficult to. And it's actually the biggest critical path to actually getting a product to market. 50% of the time is spent in hardware-software integration, trying to get the hardware, the software to talk with the hardware. So if you can eliminate those bugs, you're already increasing your time to market. Again, automation scopes, we can actually look at the hardware-software interface automation, where we're automating not just the verification environment. You could actually automate your RTL, etc. And then we're leveraging the UVM capabilities, like things like the register built-in test cases, etc. So the whole, I suppose, for that particular use case, the hardware-software interface, what these IP-XACT plus UVM gives you is a faster time to hardware-software interface qualification. Very, very quickly, if you define your registers on Monday basically in some type of IP-XACT format, run a generator, you have a test bench up and running by Tuesday, you have your interface qualified by Tuesday afternoon. If your data if you can leverage the data you even have at the moment, you can start leveraging the advanced verification capabilities of UVM, and that's the type of turnaround time that you need. The other part of this, the other main benefit, is that register specifications are not stable. They change. Things move from one register to the other. They get wider, get narrower, etc. With this, an update to us, we've seen it, and again, you can probably see it in some of the vendor presentations. Changing a register, adding a register, adding bit fields, etc. to retesting could be 10 minutes, including the simulation time. So that's the type of turnaround time you need. You don't want to be waiting for another spec increment and another verification environment increment that could take a week. You don't have a week. You basically want to get that test case run there and then. Thanks very much. Is that for me? No, sorry. So conclusion, IP-XACT UVM delivers advanced verification capabilities. IP-XACT provides a standardized way to define registers. UVM can be generated from IP-XACT. Missing UVM constructs in IP-XACT can be modeled by extensions and are also geared woven into the next standard, and you can have a significant boost in hardware-software interface verification productivity.
Okay, so I would like to give the credit of this presentation not to myself, but to Erwin de Kock from NXP. He could not be there, but most of the credit, if not all of it, goes to him. So Erwin is chairing the extension working group of IP-XACT, and Magillem is only the co-chair of it. And my name is Sylvain Duvillard, and I'm part of Magillem. Okay, the agenda of this presentation would be to give a bit of an introduction, to tell a little bit of what is an extension in a standard, and especially in IP-XACT. The main course today would be to present the area where extensions are being standardized within this working group. A quick summary at the end, and some acknowledgement of the contributors on that content, on that presentation, and on that set of extension. Okay. IP-XACT, as you have been presented today, has started some years ago, and there have been multiple release of the standard. Every release was bringing additional, let's say, possibilities, additional content, additional, let's say, benefit. So the first release of it with 1.0 was only for RTL assembly and no hierarchy, flat level. Then with 1.2, the hierarchy were introduced, and I skipped 1.1 with the timing constraints. 1.4 has bridged the gap of ESL and RTL, so it was possible to model with the same environment an ESL platform and an RTL platform. And IEEE 1685-2009 has brought some more register, let's say, features, but as you've been presented before, it's rich, it's richer, but it's not rich enough. So the principle of a vendor extension is in its name. It belongs to a vendor. So at the beginning of IP-XACT, everybody started to create its own vendor extension because they had some specific needs that were not covered by the tools or by the standard. The thing is, it went pretty well, but over the years, the people realized that they were integrating IPs coming from many places, many providers, and although it's very nice to get an XML file from your IP provider, if you have something that is very specific to you, this is very unlikely that you will get this specific content from all your IP providers. It can be even more, let's say, more than that or worse than that. If there is an extension specific to a tool vendor, it is very unlikely that another tool vendor will have the right to support it natively and openly. So this is where in Accelera the people said, okay, the IP-XACT is a standard, but it needs to have more content and to allow reuse between IP providers and between, let's say, tools. So this is the whole idea of the extension. It is to provide all the missing parts in the standard quickly and in an open and documented way so that all the IP provider can adopt it and all the tool vendors who want it can also adopt it. Okay, IP-XACT is an XML format. It's machine readable, as we've seen, and you have a very strict schema to make sure that you are placing the correct data at the correct location with the correct content, and there are semantics for that. But here and there, at multiple places in the schema, but sometimes not everywhere, unfortunately, you have a placeholder which is called the Spirit Vendor Extension. And this placeholder is there to allow you to capture what is not yet available from the standard. So this is a way to capture a user content in an official and structured document. So there are multiple places where it's allowed for someone to create additional content. And the type generator interface that is also coming with IP-XACT has an easy access to that information at that place. Okay. Now this is a typical example of something that you could get. This nice picture is the schema of IP-XACT as documented by a good XML editor, and I will join John on that. XML Spy, who created that, is a good tool. It's friendly to read, and it's a nice documentation. So the principle is that this is the official placeholder, and inside it you are free to capture a valid XML content. Now, as we say, or as I told you, companies have been using vendor extension. So multiple users or multiple vendors have vendor extension. So it is company specific, and therefore it is very difficult, or it needs a lot of treatment to capture the information. So it is very difficult to get everything for all the IP in a large SOC with all the same level of information and same level of extension in there. And remember that your automation will be limited by your weakest IP or your poorest IP in terms of content. So if you have 300 IPs, which is very common in large SOC wireless or thing like this, you need to make sure that your 300 IPs have all the extension you need with the same level of quality and all the views and everything. So it's a lot of work, and that's where maybe weeks can be spent to capture the information. And the reason why you spend effort there is because it's not yet public. So it is in IP-XACT, it is possible to capture it in IP-XACT, but it is not yet a standard. It's vendor specific. So the idea of the vendor extension, as they will be presented in IP-XACT, is to bring more functionality where it's needed, but to make it public. So as you can hear, I'm coming from the other side of the Atlantic, from Europe, and Europe has been using, let's say, a lot of IP-XACT and lots of vendor extension in European projects, and some of their work and their contribution has been brought into the extension, and that will be presented today. Okay, so the idea is to make sure that the missing part of IP-XACT today that we are working on hard to be part as much as possible of the next IP-XACT release. We want to bring it to you sooner, because if the IEEE standard takes a pace of 2 years or 3 years between every release, maybe it's not going to be UVM anymore when you need it, so let's do it sooner. So it's a kind of a lab that we can, let's say, test extension and test schemas. And please join this working group if you want to learn in detail the extension that I'm going to present, and also if you want to bring some additional aspects that you think are very important, that are crucial for verification tomorrow, and that could be part of it. Okay, so far the extension working group has tried to cover the following, let's say, topics that were not part of that are not part of the IP-XACT, let's say, generic content. So there have been some questions today about analog and mixed signal that will be covered. Some people from ST typically have brought contribution for putting IP-XACT, for getting the benefit of IP-XACT early enough in the physical design planning. Power is also an interesting part of the design process where IP-XACT was not present yet. Software or hardware-dependent software is a big story. And the last but not the least, UVM, where you have been a nice presentation from Dave. Okay, so it is about analog modeling, but analog was already, let's say, possible in IP-XACT in a lot of manners. When you are designing analog, let's say, cells, or when you are assembling smaller analog, let's say, small IP to make a larger analog subsystem, maybe you want to simulate it, you want to generate some Verilog AMS, you want to do a lot of characterization, but sometimes people now using your analog blocks, or people integrating analog IPs or PHY, they just want to take the benefit of the assembly point of view. So the first way of IP-XACT was already present was the bus interface. You can capture an analog, let's say, reference voltage with multiple voltage, multiple level, and it can be a bus in IP-XACT. So that was already covered. Connecting an analog IP into a digital world, that's something that IP-XACT knows how to do since the beginning, I would say. The extension that are here are more to help to bridge the gap between the implementation and the, let's say, the prototyping or the exploration of the analog architecture. IP-XACT was kind of poor in terms of signal because it's only 1 or 0, so it's relatively limited for analog people. It's poor in terms of, let's say, sampling. It's poor in terms of voltage versus current. It was poor in terms of, let's say, metrics that you can have. Is it ohm, picofarad? I don't know. What units can you model? So IP-XACT, and this was mostly driven from a European project joining effort of multiple companies called Beyond Dreams. And so it has modeled 2 additional, let's say, kind of information for the analog people. It has modeled the physical support that links them to the Verilog AMS or HGL AMS types. And it has also added the model for the computation associated to the port. So this is where those kind of schemes can now be supported with extension, let's say, advertised or standardized in an accelerator manner for IP-XACT. So this one is to allow in the early stage of assembling and prototyping also some design planning extension. So it's simple. It's when you have to make a trade-off in your system, the area, maybe also somewhere where you have to make trade-offs. So some information has been captured to model the width and some information related to physical planning. So the power, typically a lot of people need to derive CPF and UPF, and just as it is tedious to write UPF and CPF, let's say, by hand, it is tedious to write UVM registers. So IP-XACT has a hierarchical format, has information well structured in buses, in components, in instances. So if you capture the proper power information on your buses, all the IPs that are having those buses at the boundary would benefit from the IP-XACT power information. So this is where you capture the information at a minimum number of places, and it has impact, and it updates all your IPs without effort. So that's where IP-XACT brings things with the power. Software. So the software, there are just like we've seen that it was possible from an electronic format to derive a UVM register model, you can also derive some C code access to your register. You could prepare the skeleton of your drivers. You can, so the idea is to automate a lot of generation so that if the spec changes, you have less work to update the rest of the chain. Okay, the last is the UVM. So Dave presented all the limitation between IP-XACT register modeling and the UVM register modeling possibilities, and the idea is that all those gaps will be bridged in the vendor extension for UVM registers that will be published soon before DAC this year. And it includes the HDL pass, the randomization, coverage, and so on. As a summary, I would say that thanks to this standard extension to IP-XACT schema, you will have more possibilities from your IP-XACT files and IP-XACT flows. From one common set of data, you will be able to derive more information, and the release will be at DAC this year. The credit of this presentation and this extension should go to those people. So they are listed in a very fun algorithm order. It is alphabetic. So you can see people from multiple vendor and multiple, let's say, user company here listed, from ST, now Freescale, Duolog, Magillem, and thanks to all the people who are not mentioned here but who are contributing on the bi-weekly basis to the calls and to the standard.